Welcome to the third lecture of the Lean Learning Seminar. It's a pleasure to introduce Professor Alex Kontorovich from Rutgers University, and he will speak on an introduction to Lean and AI for research mathematicians. Welcome.
Thanks so much, Ben. Thanks for the kind invitation. And yeah, I thought I would just do a little show and tell and just try to formalize something live and see, with all the warts and all, how this thing goes. So does someone have a suggestion for a theorem they'd like to see formalized? This is going to be a experimental seminar. If no one wants to jump in with anything, I'll give people a minute. Maybe somebody will suggest something. Yes?
Sure. How about just convergence of a to the nth, where a is a number less than one or something.
Okay. I'd like to prove that a to the n converges when a is less than 1, right? So I like to do it Socratically. So I don't jump straight to give me the formal proof. I first ask Claude to give me a natural language proof, just to make sure that we're pointing its vector in a good direction. So I'd like to prove that AN converges when A is less than 1. Can you explain the proof to me? So I haven't said anything about formalization. Okay. All right. Yeah, using the definition. Let's use the definition. Um, what is the cleanest proof of this fact that I'll be able to easily formalize in Lean 4 using as much MATLAB 4 API as possible? So it gave some suggestions. Obviously, it knows this theorem. It's read a thousand textbooks that prove it. Um, all right. So the cleanest Lean 4 proof it says is this. So let's just grab it and see what's if it's right. So let me check that I have. Let's evaluate 2 plus 2. It's 4. Good. So I'm just going to dump this here. Now, you see that it imports something. And the first thing it imports is analysis specific limits.basic, which apparently actually is a file. Usually, its imports are just wrong. For whatever reason, there's so few, uh, I guess there's so little training data on which imports you need, but there's no harm in importing all of MATLAB. So I just immediately delete whatever it says. It's learned from the library, and when you are working in the library, you don't want to import the whole library because that'll be circular if you're adding a file to the library. But if you just want to play mathematics, then there's no reason not to import the whole thing. All right. So now I know what the problem is, but let's say I didn't know what the problem is. So let's feed the error message um, into Claude. So error unknown identifier n. N is the neighborhoods filter. We'll get to that in a minute. Yep. So it says, oh, we forgot to import the topology namespace. So let's open topology, and then we should have access. Um, so if I add open topology, then this is a theorem, and it's a theorem that compiles. Okay, so basically, what Claude did is it looked up the theorem in the library. It found it. It's called tends to pow at top neighborhood 0 of norm LT1. So let's open up MATLAB docs and just look at that. MATLAB docs. So I just Googled, maybe I'm going a little too fast. I Googled MATLAB 4 docs. Let me make this a little bigger. So I want the documentation for MATLAB 4. The first hit is this Lean community website. And the way this works is you just drop something in the search window here. And in this case, it found it right away. So here's the theorem. And the theorem is the following. You have a natural number k. You have a real number r. The reason there's curly brackets instead of parentheses is that you shouldn't have to give the real number r explicitly. Lean should implicitly figure out what that real number r is, given the other hypotheses. In particular, the next hypothesis is the fact that r is greater than 0. By the way, I never said that a was greater than 0, so let's just glance for a second at what it did. Yeah, it only assumed that the absolute value of a, the norm of a, is less than 1. Okay, we'll come back to that. We'll come back to that because that's interesting. It knows, it has figured out that R, okay, it has to prove somehow that the absolute value. I'm a little confused about why this works. So we'll unpack it piece by piece. So it needs to know this R, this real number R is positive. It needs to know this other hypothesis on R that it's strictly less than 1. And then filter tends to is the lean way of saying there's a limit. There's a limit at top. At top means as n goes to infinity. So it's a limit of a function. The function is a function on the natural numbers, and it takes the natural number n to the number n to the k times r to the n. Okay, so it's something even more general. Is this really the theorem? That's not the theorem we're looking at. This must be a different theorem. Let's see. I think when I zoomed in, it showed us a different theorem. So here's okay, there we go. That's better. I was wondering how it was getting from one theorem to another. Great. Here's the fact that we were actually quoting, not the one that we were pointing to. I guess when you zoom in, it changes where you are. And the other theorem is close enough. The other theorem will have either, the way it's set up is either this theorem is an immediate consequence. Yeah, it's like this kind of thing. They're all kind of close to each other. Anyway, so here we are. It's this one. So it's exactly the statement that we wanted. Namely, you're supposed to have some kind of space R, and we want this theorem to be as general as possible. So R doesn't have to be the rationals, it doesn't have to be the reals, it's just any semi-normed ring. And if you don't know what semi-normed ring is, you can always just, it's all hyperlinked, so you can click on what does semi-normed ring mean, and it extends the fact that there's a norm, that it's a ring, and that it's a pseudometric space. And if you don't know what all those things are, it's got every single assumption, every single field that's assumed here. And you can see it's a very, very long list of fields. So this is something that takes some getting used to about why when you formalize, you actually want much, much more in the list of assumptions than you would think you need in order to do mathematics. And there's a technical issue about diamonds where that this is trying to solve that maybe we don't need to get into right now. But just broadly speaking, we're assuming here that there's a norm, so just some function from a to r. There's addition, that addition is associative. We're just declaring that alpha contains a number called 0, that when you add 0 on the left and right, it doesn't change anything. Then there's ns small, which I guess is the fact that you can multiply x times 0 and get 0, and you can multiply x by n plus 1 and get n times x plus n. That addition commutes, that there's a multiplication function. Not only can you multiply by the naturals, you can multiply elements by themselves. Anyway, this is the ring. We don't need to go through the ring operations. There's a unit, and there's a casting function from the natural. There's like an injection of the natural numbers into our type alpha. So whatever, there's something called a semi-normed ring, and then there's a unspecified, again, the curly brackets mean that you don't need to say what the number x is because you'll figure it out from the context, and the context is the next hypothesis, which says the absolute value of x is less than 1. And so when Lean goes to look at what's happening here, in our theorem, which Claude decided to call Pau tends to, we took something even a little bit stronger than a semi-normed ring. We took a fully normed ring. For for whatever reason, we could have just made this the real numbers. I mean, if we said, forget about this abstract notion, alpha is the real numbers. So Lean knows that the real numbers are a semi-normed ring and that they're a normed ring, and all of this stuff gets handled under the hood completely automatically. So we have a real number A, we have the hypothesis that A in absolute value, and Lean knows that there's an absolute value on the real numbers, is strictly less than 1. Then the function that maps a natural number n to a to the n, that's our sequence. That sequence at top means as n goes to infinity, converges to 0. So it's the neighborhood of 0. And this is using the formalism of filters. Should I say more about why filters and what filters are and so on? Is that something that's familiar to people, or would you like me to give a little exposition of that?
Be good to say a little bit.
Okay. So
Thanks.
luckily, I not so long ago gave a lecture on filters, a little crash course on filters. This was in, okay, I know how to find this. So Lean Community Blog, that's the one. Lean Community Blog. We had a meeting at the Simons Foundation, and all of the lectures were recorded. And where's my lecture? Algebra lecture 2, analysis lecture 2, filters. Beautiful. Okay. So here's a little crash course on filters. So let's think about the squeeze theorem. The squeeze theorem says you have 3 sequences A, B, and C. They're maps from the natural numbers to the reals. And A is less than B is less than C for all n. And A goes to L and C goes to L. And so B has no other choice. It's squeezed between A and L. It's a sequence that's going to go to L at infinity. Okay, that's the squeeze theorem. But wait a second, there's another squeeze theorem. If A, B, and C are real valued functions, not sequences, but real valued functions, and there's some point, and I guess as x goes to x0, there's some point x0, so that an goes to L at x0 and cn goes to L at x0. Here's the image trying to illustrate that. Then B has no other choice. It's squeezed between A and C, so it also goes to x0 at L. So that's 2 squeeze theorems. And here's another squeeze theorem. A, B, and C are, again, real valued functions, but now it's as x goes to infinity, we have the squeezing phenomenon, and so on. And here's another squeeze theorem. There's a left-sided limit and for A and C at x0. And so B is also just from the left being squeezed. Like you do not want 17 squeeze theorems in your theorem prover. There's got to be a better way to handle this. And it turns out that there was a better way to handle this that was worked out by Bourbaki. And to explain what that is, let me make the analogy to topology. So, the first time you encounter topology, it's probably in the context, as a kid, in the context of a metric space, where you say a point is in the interior of a set if there's an epsilon ball around it inside that set. And then you define a set to be open if every point if every point is an interior point, if every point contains a neighborhood around it. And then you do a computation. You say there, finite intersections of opens are open and arbitrary unions of opens are open, and the empty set and the whole space are open. So those are all consequences of the definition that an open set means having an interior, that every point is an interior point. And then Hausdorff comes along and says, well, actually, there's a much better way to do topology. What you should do is just give yourself an arbitrary collection of sets that we're going to declare to be open and add as axioms that the empty set and the whole space are open and that finite intersections are open and that arbitrary unions are open. Okay, so that's just the better way to do topology. And that, of course, is taken off. I'm preaching to the choir. Everyone knows this. Well, the same thing happened with filters. The same thing happened with limits. With limits, Bourbaki in the 1930s figured out a better way to do calculus. So let me slow down just a little bit. Here's how you might instantiate that, the kind of class that you would define for topology. So you have just an arbitrary space X. In fact, maybe instead of maybe it shouldn't be type theory, it should be space theory. You should think of the word type as just space, because that's exactly how mathematicians use that word. So X is just some space. We have a function from subsets of X to prop, true or false, yes or no, this set is open. So that's this. We're declaring a type class where we presume the existence of a function called is open that will tell us whether a subset of X is open or not. We hypothesize that the universe. So uh, yeah, I don't know how many talks on lean or type theory the audience has had. Does everyone know why you want the universe? No. Okay, great. So sets. Can I write on this? Let me try to write. Annotate. Okay. So what is set X? Set X. X is a space. So that's a different kind of thing than subsets of X. What are subsets of X? The subsets of X, so set X, is nothing but is the same thing as the maps from X to prop. So an element of type set X is a function that takes X and returns, it takes a point of X and returns yes or no. You know, if here's my space X, here's my whole space X, and then there's a function that's true on this set and false on that set, and that's what it means to be a subset. Okay, and so when you say you want the whole space, you want all of X to be open, well, this doesn't take the whole space. It takes a map from X to prop. And so there's a map called univ. There's a map univ of type set X, meaning it's a function from X to prop. And it's defined by univ of X for any little x. Univ of little x is equal to true. Just take every point. Okay, so that's why there's a universe of type set X. It's just it's kind of this is part of how type theory gets away from Russell's paradox, is that you can't X can't be a subset of itself. These are different things. Subsets of X are functions, and there's a function called the universe, which represents in our mind the entire universe, meaning X. But anyway, so there's this universe function. This hypothesis says that the universe function is one of the universe set, the entire set of X is indeed open. Okay, so that's the hypothesis. And then finite intersection says if you have two sets S and T and they're both sets and S is open and T is open, then the intersection of S and T is open. And then arbitrary unions. If you have any indexing set, so iota is a set of sets of X. Okay, so it's a set of subsets of X. And if for every element in this set of subsets, the subset itself is open, then the entire union over all of the sets of those sets is open. Okay, so this is the lean way of saying what you already know about what it means to be an abstract topology. Any questions on this? Does this make sense? Sounds like it's okay. All right, so what do you do so that you don't have 30 squeeze theorems? The key idea, oh yeah, so here I'm describing the fact that set X is the type of all functions from X to prop. X is not a subset of itself. Univ is the function that maps X to all, I was saying zeros and ones, trues or falses, so these are the ones. And so how do we do, what's the right notion of a limit? So let's warm up by first going back to a metric space. So the idea is you want to, when you take a limit, you're zooming in on, let's say a limit at a point X here, this little point X. So the idea is you're zooming in along arbitrary open sets. So that's the definition of the neighborhood filter. So this n of X, given a point in a topological space, is this n of X is the collection of all sets of X which contain an open set containing X. So let me draw that again. So I have some point here, X, and I just look at some open set and then any set whatsoever. It can be as crazy as it wants as long as it contains an open set containing X. And the collection of all such sets, is what's called a neighborhood filter. So it's something very, very elementary, very abstract. I mean, it's not that abstract, uh, but that's the kind of elementary definition of neighborhoods. If you already have a topology, as you'll see in a minute, we don't actually need topologies in order to be able to take limits. Um, and then what you check, given this definition, you check certain hypotheses. So for example, is the universe in the filter? Well, the universe is an open set in a topological space, and it contains everything, so it contains the point that you're interested in. So yes, the universe is in the collection. You check that the collection is closed under finite intersections. If you have finitely many sets, each of which contains an open set which contains X, well, those open sets, their finite intersection is an open set that contains X. And so it's closed under finite intersections. It's also closed, this neighborhood filter is also closed under inclusion. And now that is the abstract definition of a filter. It's something that satisfies the same criteria, the same axioms as which were theorems for a neighborhood filter. So here's how you define a filter in MATLib. First, you have a set of sets. So these are subsets of X. So this is a filter which you can think of as the neighborhood filter, but you'll see in a minute that it's a little bit more general than that. So sets as a set of subsets of X with the hypothesis that the universe filter, the entire set, is in the set of sets. It's closed under finite intersection. So if S and T are sets which are both in this set of sets, then their intersection is in the set of sets. And we have inclusion. So notice that this makes no mention of open. This makes no mention of the topology on X. It's a more abstract notion. The inclusion is that if S is a subset of T and S is in the filter, then T is also in the filter. Okay, does that make sense? And now you can speak about all kinds of other filters. So for example, there's a filter called the neighborhood, the right neighborhoods filter, which means you take X and you insist that this contains all sets that are open and intersect the one side with X. There's an at-top filter. The at-top filter, which is what we were looking at, is all, so I'm drawing this point here, but it's not really here. This is the point infinity. And it's all sets. The at-top filter is the filter consisting of all sets that contain a set of the form A out to infinity, all one-sided intervals. So the one-sided intervals are open sets, and anything that contains a one-sided interval, including the entire space itself, will be in the filter, and you check that that filter is closed under finite intersections and under inclusion. And that's how you can speak in one fell swoop about all of these different squeeze theorems become one squeeze theorem. There's a co-compact filter. The co-compact filter is when you say, absolute value of X goes to infinity. So that means X either goes out to plus infinity or minus infinity, or if you're in an abstract space, what it means is you leave compact sets. So it's the complements of compact sets. So the co-compact filter says a set is in the co-compact filter if it contains the complement of a compact set. Okay, and that's the entire filter. So does that make sense? So again, this was introduced by Bourbaki, I think in the 30s, analogously to how Hausdorff changed topology. And in certain fields of mathematics, this is well known. And in analysis, and the place where you would think this would be picked up the earliest because it's most applicable, it's somehow people just stuck with epsilons and deltas. So it's a historical thing that, like in p-adic analysis, everyone uses filters. They're just more convenient than trying to use epsilons and deltas. And well, I think in the future more people will use filters. They're actually a better way to do analysis. Anyway, so in the same way that metric balls are unnecessary for topology, use the abstract notion of open sets. Topology is unnecessary for neighborhoods. Use the abstract notion of a filter. And now, what does tends to mean? How do you get the notion of convergence in this general setup? Let's think about, well, it's the same thing as the notion of continuity when you have an abstract topological space. an abstract function is continuous if the pre-image of an open set is open. And in the same way, um, this is almost right. It's not exactly how it's implemented in MATLib, but as to a first approximation, you can think of it this way. How to say that f tends to a neighborhood of, let's say you have a point x that gets mapped to y, and you have a neighborhoods filter at x and a neighborhoods filter at y. How do we say that the function from x to y tends to y near x? You would the way to say it is that for all sets in the neighborhood of y, the pre-image of that set is in the filter for x. And so this is the tends to function. You have this is the definition of tends to in MATLib. This is a I'm slightly lying here, but don't worry about it. You have a function f from two completely abstract spaces. They don't have to have a topology, nothing about them. But I have a filter on x and I have a filter on y, and we say f tends to sends one filter to the other if for all neighborhoods in the neighborhoods of y, the sets that are neighborhoods of y, the pre-image is contained in the neighborhood of x. And so this allows you to have one squeeze theorem. There's one squeeze theorem in MATLib, not 17. And here's what it looks like. So this is the actual squeeze theorem that I grabbed from MATLib. Of course, it has one of these MATLib names, tends to of tends to of tends to of LE of LE. And what it says is you have abstract spaces alpha and beta. Yeah, if we're going to talk about the neighborhoods filter, then we actually do want to introduce topological spaces. So I lied a little bit. But we have a topological space and we have a way to discuss order. I need, A less than or equal to B is less than or equal to C. So I do need at least a pre-order on alpha, and that the topology induced by the order respects the topology of the topological space. And I have three functions f, g, and h from beta to alpha, and I have a filter on beta, and I have a point a in alpha. Then, and I assume g is always less than or equal to f, and f is always less than or equal to h. I know that g tends to the filter b near a, and I know that h tends to also be in the neighborhood of a, and from that I conclude that f tends to the filter of b in the neighborhood of a. So that one squeeze theorem in MATLib covers all the 17 that we just in natural language have no trouble going back and forth between. Okay, does that make sense? Any questions on this generalization? It takes doing, please. Please go ahead.
Uh, sorry. It looks to me like this doesn't handle the case of a limit as x goes to infinity, because there's no point A in the domain.
That's right. So it doesn't, and I guess maybe the reason it doesn't is because then all you need is a lower bound. I mean, if you're going, yeah, if you that's right, yeah. So if you were trying to do a squeeze theorem and your point is infinity, then, well, I guess as long as the lower bound goes to infinity, then you're being forced out to infinity. You don't need the hypothesis of the upper bound, and maybe actually there must be. Let's see if we can find this. Tends to of LE of LE. There's going to be a different theorem that handles that case. So tends to. I'm just going to write some nonsense, and this is the better way to find things in the libraries, just to start writing a bunch of letters, and it will show you everything that includes those letters in that order. At some point there's an ends to, eventually tends to. That's not what I want. It's this first one. This first one is the squeeze theorem. Now, where's the squeeze theorem at infinity? These are all different versions of the squeeze theorem with different hypotheses. So for example, this one only hypothesizes not that G is always less than or equal to F, but that eventually in the filter, yeah, we didn't talk about eventually yet, but let me come back to, you don't need F and G to F and H to always be less than or equal to your function F. You just need in a neighborhood of where you're trying to take the limit for that to hold. And so that's this stronger version.
Alex, can you
Okay,
hear me?
you don't have to find the other version. I just wanted to make sure I was understanding correctly that
Yeah,
this is not all squeeze theorems, but
you're absolutely right. I'm making the case that it contains all squeeze theorems and actually doesn't, because the squeeze theorem at infinity is a different squeeze theorem. It's just a lower bound theorem. You don't need to be squeezed from the top.
well, if you're talking about a finite limit at infinity, you probably do.
Uh, if you're talking about a finite limit at infinity, in other words, if the picture I have in mind, whether it's at infinity or at a finite point, I have some h and h is blowing up
But what if
and f is above h.
yeah, what if f and g are not blowing up? F and g both go to a limit L as
Okay.
x goes to infinity, and h is squeezed between them. That would be another squeeze.
So that's contained. That is so the target is a point, but the domain is actually an abstract filter. So this does handle the case at as x goes to infinity.
Oh, I'm sorry. So I misunderstood. I thought
Yeah,
A,
what it doesn't happen is the y being infinity.
yeah, okay. Okay.
So I'm worried about the function blowing up. So like if I'm going out to infinity and h is blowing up and f is doing whatever, but it's staying above h, then f also has to blow up.
Yeah.
But then I don't need an upper bound.
Right. Okay. Thank
So
you.
it is a genuinely different squeeze theorem if the lower bound is blowing up.
Alex, can I ask a quick
Please.
question? This is Mike. Thank you. But this solution to 30 different squeeze theorems, this is kind of special and ad hoc, right? In other words, it takes some good thinking, like Bourbaki thought about it and figured out a clever way, 50, 80 years ago. But mathematics must be full of this situation where you have like 50 different ways of saying approximately the same thing. And it would be wonderful to have a steamroller that like flattened all that out. But how's that going to work?
That's MATLib. That is exactly what MATLib is trying to be, is to be that steamroller. It wants the most abstract notion of everything. It wants, it does not want to have 17 versions of the squeeze theorem or
Uh,
any theorem that has lots of different versions. So
I
that's
see. So
why
it's
it's
going
so
to force
general.
us. It's going to force us to think very abstractly, um, which is good for some people who are inclined that way. But Freeman Dyson talked about the birds and the frogs, right? And some people want to think very narrowly. And how will formalization work for them?
So what there needs to exist, uh, for me, MATLib is an engineering project. It's not an educational project. It's not um, a place to learn how to formalize. It's not a place to learn what the mathematics is of formalization. What we need to have is on top of MATLib should be like a wiki
Mm.
that explains what to do for the. And I also I don't know. I try to go between the frogs and the birds, but uh,
Yeah.
but I spend a good amount of time in the mud with the frogs,
Okay.
and
Okay.
and I. If you told me 5 years ago that I would enjoy making things more abstract, I would think you're completely insane.
Yeah, yeah, no, I mean, I think this is beautiful because abstraction has its place, but sometimes you have to work in the mud. So, yeah, I
Yeah.
love it. Thank you.
Yeah, so we need more educational resources that allow people like me. I mean, I struggled when I first learned this. I'm like, why are
Yeah,
you doing it this
no,
way? I know how to
no,
prove it.
it's amazing. It's amazing.
Yeah, but then
Great.
you realize that it's just better engineering, and so that's
Mm,
why it's there like that.
yeah.
And so maybe in the future, when this becomes commonplace, we'll all just know filters in the same way that we all know topology. There's a very funny historical reason that
Mm,
topology took off the way it did from Hausdorff, but filters didn't take off in all subjects of mathematics. Again, in some subjects, this is very well known in some branches. Um, yeah. So you're absolutely right that we need both the engineering to be able to do these things and to do them at scale, and it would be nice to have an educational resource on top that explains what's actually going on to the rest of us.
right.
Yeah. Any other questions, comments? Yeah, so let me just say one last thing, which is about the eventually filter because it came up. Right, so the point is we don't need F and G and H to always be upper and lower bounds for F. It's enough um, to speak of one-sided limits, and that's the eventually filter. Anyway, maybe I don't need to. Yeah, the point there was I was going to give people a bunch of exercises, so you actually get to get your hands dirty with these definitions. but we're not going to do that now. So let me go back to what were we doing? We were proving that, right, that if A is less than 1, then the sequence A to the n goes to 0, and here it is. So it's filter tends to. In fact, we can make this look a little bit nicer by opening filter, then we don't need to write filter everywhere. So at top, and it'll figure out what the type is, and maybe I'll make it look a little nicer. Okay, so this is like the nicest version of this theorem that I could probably write down. You have a real number A, it's in absolute value less than 1, and A to the n, as n goes to infinity in the natural numbers, goes to 0. So there's a tends to from the sequence A to the n in the at top filter as n goes to infinity, and the neighborhoods filter of 0. Did that answer? I forget who asked the question about if the absolute value.
Yeah, yeah, very well.
Should we try another one? We have time. Let's try another theorem and see what we can.
Sure. Actually, I have a question. So
Please.
there are a naming convention in MATLAB, like all the names are so messy, I guess.
So the naming convention is that what you want, there's a very long and complicated naming convention, and there's lots of arguments on Zulip about what the right names of things should be. The idea is, in fact, that the naming conventions, of course, were invented long before LLMs became a thing. But the naming conventions, it turns out, are such that LLMs can be pretty good at guessing names of theorems. So the name of the theorem should basically correspond to what's going on. So why is this called tends to of tends to of tends to of LE of LE? The first thing, the tends to, is the conclusion. The conclusion is a tends to statement. So we're gonna derive a limit from of tends to of tends to. So there's another tends to and another tends to of LE of LE. And there's a less than equals and less than equals. So the information that's hidden in this name is that I'll give you a tends to if you give me two certain tends tos and two LEs and LEs. Give me two inequalities and give me two limits, and I'll give you another limit. That's what this naming convention refers to.
Okay, thank you.
Yeah. How about something else? Ben, we were trying to, what were we doing? We were trying to show that if like y prime is equal to y, let's solve a differential equation, right? That would be a nice, if we can do it. I don't know if we can. Well, this will be an experiment. Okay.
Great, thanks.
Yeah. Let's try to solve the differential equation y prime equals y. First, do it in natural language. Okay. So the key insight is to, well, so, right? That's the general solution. That's the interpretation. Can you give me a solution which will be easy to formalize in MATLAB 4? I accidentally said MATLAB 5. I hoped that there won't be a MATLAB 5. Yeah, okay. So it's suggesting the following. The first thing it says is the function e to the x times a constant has derivative e to the x times a constant at the point x. Okay, let's see this. Let's see if this works. The uniqueness is the key part, of course. So let's just try. I'll go down here. It's not, what's there isn't hurting anybody. We don't need any more imports. We've imported everything. So let me comment this out so that we don't get errors and just put a sorry in here. All right. So first of all, it has misstated the theorem. It says, given this constant c has derivative at, so if you hover over has derivative at, you'll see what it says. It says that f has derivative f prime at the point x. So you have to give me a function f from some non-trivially normed field k. Could be the real numbers, could be the complex numbers. You know, you again want to work in generality, so you're not repeating statements. This could be any kind of function, any kind of domain that's a normed field. Normed field, well, field, I need to be able to do things like add, subtract, multiply, and divide. And normed, I need to be able to take norms, so I can say f at x prime, if x prime converges to x, is equal to f prime times x minus x prime with this error. So give me what you think the derivative is, what the value of the derivative is, and give me a point. And then I'll say has derivative at f, which is a function, f prime, which is a value, and then x is the point at which that value takes place. So that's what Claude is trying to do. It's giving us the function. The function is a function that sends x to this constant times e to the x. It's giving us the hypothetical value, a constant times e to the x should be the derivative of e to the x, and that should happen at the point x, except there is no x in the context. So let me spare Claude the embarrassment. I'll add an extra real number x, and now there's no problem in the statement. But if you didn't know that, let's just see. We have an error message, and our error message is unknown identifier x. So I'm just going to copy that and go here and say in exp solves, what do they call it? Exp solves deriv eq. In x solves deriv eq, I guess in the statement of this, I get an error, and here's the error message, unknown identifier x. You, Claude, need to explicitly introduce x as a parameter. And now I've figured it out. You should add x as a parameter, because otherwise it doesn't know, what to do. Okay, so now we at least have a statement, and we can work on proving this statement. So we want to show has derivative at the function that sends x to c times e to the x. Let's open real. Let's make this look a little nicer so we don't have to keep writing real dot everywhere. Oh, what happened? I said real and then it jumped somewhere else. Okay. So now it really looks, because there's a real exponentiation, there's also a complex exponentiation. So we have to specify which we want. So this will now know that we mean the real exponentiation. So the function that sends x to some constant times e to the x has derivative constant times e to the, maybe I'll call this, just to make it a little clearer what's going on, I'll call this x naught. And then the derivative will be e to the x naught times the constant, where at x naught. Okay, so this is a dummy variable, whereas these are not. And what it says is, first we should rewrite mul1 x. Oh, but it's not x, it's x naught. So let's see if that is true. Okay, so what is it doing? Mul1 says that you can multiply by a times 1 equals 1. For some reason, it wants to say constant times e to the x times 1. Okay, I don't know why, but that's what it's suggesting. And then the next thing it wants to say is exact. So it's going to try to one-shot it. Has deriv at const mul has deriv at x. I'll make it x naught and then c. Okay. So what it's trying to do is it's trying to chain a couple of things together. So there's a function called has deriv at x. There's a theorem called x deriv at x. Let's find it in the library. Why can't I see the library? Here it is. Okay, so has deriv at x is the statement that we want. So in any norm space, you can have an exponential function in any norm space, and the derivative of that function at x is e to the x. So that's a useful theorem. That seems like a useful theorem. Let's get that into our little context here. I'll just say have. Let's have this theorem. And you see what we got is a new hypothesis called this. And this says for any real number x, we have this derivative. I want this at x naught, so I'll feed it x naught. X naught. Okay, so now we know, and Rexp is Lean's shorthand for the real valued real dot exp. So the derivative of the exponential function at x naught is e to the x naught. Great, of course that'll be useful. And then we want to have that multiplication. I don't know why it did this rewrite. I think this rewrite was a mistake. I'm going to use executive privilege and comment out that rewrite because that's not what we want. What we want is use this const mul. So let's look up this has-derivat.constmul function. What does that do? Has-derivat.constmul says, if you know that the derivative of d is d prime, and you have a constant c, then the derivative of c times d of y is equal to c times d prime. So let's try to just isolate this theorem. I'll just have this theorem, and it's stuck because it says type class instance problem stuck. It's often due to meta variables. It doesn't know what kind of normed algebra. What do I have to give? I have to give a constant. The first thing that doesn't have curly brackets in the statement, these are curly brackets. This is type class inference. I'm stating that K is a non-trivially normed field. Again, maybe the real numbers, maybe the complex numbers. But then I need to be given a normed ring, and C has to be an element of that normed ring. So what constant am I trying to multiply by? Capital C. So if I feed into this theorem, capital C, it should be able to work out, well, almost everything else, but not quite. It probably still doesn't know. Once I feed it capital C, it knows what A is, and it can fill in all of these things about A. But what it doesn't know is what is K. And the next thing it wants is a derivative statement, has derivative at d prime dx. That's exactly my previous statement, is this. This is the has derivative at statement. So let me feed it this. And now it says has derivative at, the function that sends y to c times e to the x is c times e to the x at x naught. So that's exactly what I want, actually. So exact this will do it. All right. So we've solved one goal. Is this clear what I'm doing? I'm moving kind of quickly, but hopefully you're getting a sense of how to do this kind of thing.
Okay, sorry, I have a question. So
Please.
does the new this, cover the old this, the two halves?
Great question. So the old this is dead.
Mhm.
So a better way is to just name your hypotheses. This is H and this is H prime. And then they have names. They have names H and H prime. Of course, it's not called this anymore. It's called H. And this isn't called this. It's called H prime. And now we don't have that problem. So here I have H and I have an H prime. So this, I use this if I'm just throwing out have statements and I don't want to name things. An old friend taught me you don't name the cows on your farm because you don't want to have to eat Sally. So you don't name have statements you're going to throw away. If you're going to use it somewhere, if you're going to use it immediately, you can call it this and then forget about it. But if you actually want to use it throughout your argument, just give it a name. Yeah. So if in fact, if I give them the same name, we'll still have the issue that the old H is dead. I can no longer refer to the old H. So give them distinct names if you want to keep them around.
Okay, thank you.
Let's play one very quick round of golf. So this would not be a good proof in MATLib because there's no reason to say exact H. I can just say exact this. And meaning I don't need H at all. And then do I need to refer to H or can I just stick in what H is in place of H? So now we have that and I don't need this line at all. And by exact, there's no reason to go into tactic mode if I've already created the term. So this is what happens. This is why MATLib looks the way it does. People are constantly, scrunching their proof. And now the reason the derivative of constant times e to the x is constant times e to the x is has derivat dot const mul c of has derivat x0. And now you can't tell anything that happened to get to that line, but that line is now in the library. Does that make sense? This is the kind of thing that goes on to create the library. Okay, but that's not what we wanted. That's not a solution. That's just an instance of a solution to that equation. We want to solve the equation. So where was that? That was up here. We want uniqueness. Oh, interesting. Okay, so it says all solutions. It says that there's a function that this is a theorem in the library also. Haha. So it lied. This is what LLMs do. They lie. So it suggested a theorem called all solutions are exp. It says f is a function from the reals to the reals, and notice it's in curly brackets because we should be able to figure out what f is in context. X naught and y naught are two real numbers. HF is the hypothesis that for all x, the derivative of f at x is f of x. That's exactly the equation we're trying to solve. And we have this hypothesis 0, some anchor, that says f of x0 is y0. Then there exists a constant c, so that for all x, f of x is a constant e to the x times x minus x0. Great. That is the correct, it correctly gave us the statement that we want, right? And hopefully we, without really too much lean knowledge at all, this should just read like mathematics. We don't need the real dot. We can make it even slightly nicer. But the problem is, it says there's a theorem in the library, and there's not that theorem in the library. So it hallucinated the name of a theorem which doesn't exist. So I'll tell it, let's move on to, what was this called? All solutions are exp. Error, I'll just say error. Unknown identifier. You made up the name in the library. Let me give you a more realistic approach. Okay, now it's going into a proof. This is good. I think this is good. It's giving us a proof instead of trying to quote something in the library. Using what's actually in MATLib. Yes. Ha. The reality is that proving uniqueness of ODEs from scratch in Lean 4 is quite involved. I'll say, can you look up how this is done in the library? So this is RAG, Retrieval Augmented Generation. Claude will do a Google search, and it will add to its context. It'll figure out what it wants or doesn't want. So it's looking at ODE solutions, differential equation solutions. We can open this up and see what various searches it's doing. We can look at what the results are. It found something in I have no idea what these. It's trying to find some strange websites and pull whatever it can. Based on my search through the documentation, I can see that the library approach is different from what I initially suggested. Here's how it's done. Okay. So we know that this is just saying that what we already knew. The key insight is that the reality is, yeah, this theorem doesn't exist. Instead, you'd work with general ODE machinery and something called the Gronwall module. No, okay. So it did give us something that looked good to me, which was this. Let's try this. Let's try this. I think this is a good approach to this problem. And maybe the lack of time will put me out of my misery, but let's just try it. So let's go into the proof. Okay. So what's the approach? Let me just tab this over a little bit. We're going to make a new function called g, which is the function that sends x to f of x times, we don't need the real anymore, e to the minus x. Okay, and then we want to show that g has derivative 0. So suppose we could show that g has derivative 0. I'm going to just comment all of this out and say, sorry. Suppose that we could show that g always has derivative 0. Then g is a constant. So it's saying that there's something called is const of deriv equals 0 in the library. Maybe there is, maybe there isn't. Let's find out. So let's go back into the documentation and say is const of, here it is. Look at that. Is const of deriv equals 0. There really is such a thing. Okay, let's grab it. Let's grab it. This is great. So there's a theorem. I'm just going to say have colon equals is const of deriv equals 0. Of course, it's going to be stuck until I say more. What is the first thing it wants? It wants the differentiability of the function. Now, do we ever assume that f is differentiable? Well, kind of. The fact that it's the fact that it has a derivative means that it's differentiable. But let's just record that fact. So let's say have f differentiable. I want to just say differentiable. over the reals, f. Why is that true? Let's come back to why that's true. That should follow from the fact that if it has a derivative, then it's differentiable. So if I feed that to this thing, it says, oh, but it's not f, it's g that I want to be differentiable. Okay, so let's record the fact that f is differentiable. Let's record the fact that g is differentiable. And let's feed that into g. And then it says, if we know that for all x, the derivative of g is 0. So instead of has derivat, well, okay, let's make an alternate version of this statement. You see, I'm just hacking together something that approximates proof. Have deriv prime for all x, deriv g at x is equal to 0. And let's just sorry that for a second. So if I feed hg deriv prime into this, now we get that for all g of x, for all x and y, g of x is equal to g of y. Great. And we want to know that there exists a constant so that for all x, g of x is equal to that constant. So the constant is just x0. Well, I'm sort of, instead of iterating with Lean, with Claude, I'm now going into the proof. But let me try to go back and forth with Claude a little bit. So here, all I'm going to do is grab this entire info view, copy it, and where was Claude? Over here. What do you recommend for the next step at this goal state? And I just dump it in there, paste. So I've pasted in, it knows that we have a function, it knows we have points x naught and y naught. We're very close. We have the fact that g of x is equal to g of y, and so just use g of 0 for the constant. Our goal is to show that there exists some constant. What constant should we use? How about g of x0? Did I not copy it? How about g of x0? Okay, now we want to know that for all x, g of x is equal to g of x0. So also give me an x, introduce an x. That's the next thing that it suggested. Intro x. Great. And then how do we prove this? This is just this. So exact this applied to x and x0. Okay, now we've proved that g is a constant. And now let's extract that. I mean, this isn't the slickest proof, but it's a proof. We're going to extract this constant. That's g const. Use c, intro x. We have this. And so what? We're basically done. We have that f of x is equal to f of x times e to the minus x is equal to that. And then solve for f of x. So how do we solve for f of x? Let me just give this and ask what's the next step? What's the next step here? I want to multiply. Okay, it says first let's have the fact that yeah, it does x pos. Let's see. I'll give it one more line and then see if it can finish it. Unknown identifier, x pos. I think that is something in the library. Okay, it's called real.xpos, not rxpos. Okay, but it still failed to find a contradiction. Field simp at this. No, it thinks that it's dividing. The reason it's trying to call it field simp is it thinks it has f of x divided by e to the minus x, but it doesn't. Anyway, time has run out, so I think I will just say, sorry, and comment that out. And this hopefully gives you some flavor of what it's like to try to do some very basic analysis where you're not just the moral of the story is that if you don't know any lean, it's okay because as long as you have access to something like Claude, you can get started and start proving some simple things. It might start telling you things like filter, and then you have to learn or get a little bit of practice with filters. But otherwise, it really should feel like doing regular math, at least when you're doing things at a undergraduate level. So let me stop there. Thank you.
Okay. Thank you for the very amazing talk. Any questions from the audience?
Hi, actually, I have one question. Sorry, let me turn the camera on.
Please.
How oh, camera's not working that well. So how would we like for example, if we're using like cloud or any other AI to solve like an inference problem, like if this is like especially like convoluted like instant reference problem, and then I tried cloud before, but it doesn't. It sometimes just stuck throughout, and you put in and you give them, oh, okay, figure out how to do this, and I just said like, yeah, something is not working.
So this iteration process does not always work. I mean, unfortunately, the our current AI systems, as you see, something as basic as this, um, the combination of how difficult formalization is and how difficult it is for LLMs to say the right thing, because they're just spitting out tokens. You know, they don't. We tend to see all kinds of amazing behavior out of them and give them maybe the benefit of the doubt that they actually know what they're doing, and then you see what they do for a formal example like this, and it turns out they actually don't know anything, but they're really good at search. So they can find they're quite good at stating things. Of course, you still have to check yourself that it stated a theorem that you think is true, and that theorem says what you want it to say. Uh, it's very good at pointing you to the right kinds of concepts like has deriv at and rexp or real.exp. Um, but it's a struggle. We are uh, I was about to say we're very far from these systems getting very good. Although if you told me 6 months ago that it would be as good as it already is, I wouldn't believe you. And 6 months from now, it might solve everything. So I don't really believe that either. But in terms of formalizing undergraduate mathematics, I think in 6 months it's going to be much better at it than it currently is. The pieces
Nice.
are all there. They're just not perfectly gelling.
Alex, can I ask, motivated by your filter example,
Please.
would it be possible to have a bot crawl around MathLib and suggest that there might be a missing abstraction that we haven't thought of that could simplify things?
Absolutely. Yeah. In fact, there's not quite to the level I think you're envisioning, but there's already a bot that, for example, crawls around, and if there's a theorem that's proved by rings, proved about rings, the bot checks if it could also be proved by semi-rings. This kind of
I
thing,
see. Okay.
this kind of thing that as human beings is like, oh God, who cares if it's true for a semi-ring? But then you encounter some situation where an application, you actually have a semi-ring, and obviously you don't want two theorems if
Yeah. Well,
yeah.
no, yeah, that sounds good. But
But it-
something I noticed in your exponential example is Claude seemed to worry a bit about whether the function was differentiable or not. And that made me think that that might be a case where extra abstraction actually might slow you down because you can have distributional value derivatives. So you could
Right.
like a piecewise linear function, and in some context it has a derivative, and some it doesn't. And I just wonder whether that would be an example where too much abstraction actually makes the proof slower. Because when you talk about a derivative, it's not clear if it's a distribution or a function.
Right. So the way derivatives are handled, so I don't actually know how, let's ask, how are how are distributional derivatives handled, if at all, in MathLib? That's a good question. I don't know that part of the library. But the different so they have Fréchet derivatives for has deriv at is the Fréchet notion. It's something very general. Has derivat filter, okay. And what is has derivat filter? It's um, continuous linear map, small right. Okay, so um, hmm, where's a good place to, okay, so f deriv within deriv. I want to see an f deriv. I want to see an f deriv. Okay, so has f deriv within at. Right. So here we are. So I think this is one of the more general differentiation theorems in the library. It says you have a non-trivially normed field K and just some topological space E that's a K module, so some, vector space, and another vector space F. So what is the derivative? The derivative is a linear map from the vector space, the target vector space um, to the range, and then you have a set S, and we say that a function F has derivative F prime if this, I mean, just the usual F of X prime is equal to F of X plus F prime as a linear map on X prime minus X is little o of X prime minus X inside the set S. So
Yeah, so they don't consider distributions here.
this
Yeah.
right now
They
is not
Yeah, they're just not there.
this isn't there, but there are weak derivatives, so there are partially so, but the treatment is limited. Okay, so distributional derivatives are not yet fully implemented in MATLAB 4.
Okay.
That's what it seems to be the case right now. These are actual derivatives and not distributional derivatives. Yeah,
Okay.
so
Ben will probably need those soon if he's going to go through singularities.
absolutely. Yeah,
Yeah.
that could be a good warm up. In any serious project, you need all kinds of stupid little warm up projects that aren't that stupid at all, actually. And it turns out that you learn, at least I learn a lot of mathematics, even when I formalize things that I thought I already knew.
Yeah.
Because this kind of work really forces you to um, not repeat arguments and try to, axiomatize everything that's going on, because it's just easier to prove abstract theorems than it is to prove concrete theorems when you're working formally.
Great. Well, I love this lecture. Thank you so much.
Thanks, Mike. I appreciate it.
Okay, any other questions?
Yeah, maybe can I try throwing out a sort of provocative
Please.
Counterpoint to the previous question? So on one hand, right, humans benefit from all this abstraction of not having 17 versions of the squeeze theorem. Is it possible that the LLMs, that we want to do automated reasoning actually prefer 17 versions of the squeeze theorem that are analogous, and so that way they can sort of learn from the similarities between them?
Yeah, so that's a great question. MATLib is not being built to help LLMs. But I think what people do in practice when they train LLMs is that they take the squeeze theorem that exists and then they write another one for the reals, and they write another one for the complexes, and they write another one for, they write out those 20 versions of the squeeze theorem as part of the training data for their LLM. So that's something that people do regularly. You have 10 different ways of stating something. They're going to turn it into 100 different ways of stating something and send all of that into the training data for the LLM. So
And that's very easy to generate from MATLib because you can just like expand.
yeah, just instantiate.
The proof.
Yeah, you have an abstract theorem. You can instantiate it for the reals. You instantiate it for the complexes. You instantiate it for, a normed vector space. Whatever. So that is absolutely, I think, an important component, and it's what people do when they're training their LLMs. I don't think it's what we want in the library, precisely because imagine you have to, multiply any theorem by 17 in the library. Well, all of a sudden, when you get to 10 million lines of code and 100 million lines of code, now you need 1,700 million lines of code to say what you could in 10 million.
But in the short term, that might be coming, right? Because if we get to a point where people are really using LLMs to help formalize, then what we're going to be getting is sort of inflated in that way. And so, how do you sort of tame that complexity in MATLib, in some way that's actually sustainable?
So the inflation happens at the level of training data for the LLM. That inflation does not go into MATLib.
No, but I mean, like I'm saying, the next generation of, I mean, right now people are writing MATLib sort of by hand, but that's clearly at some point that as we climb up the abstraction ladder, we probably have to start, using LLMs to help actually construct MATLib. And at
Absolutely.
that point, now the code is going to be more inflated because the LLMs are not necessarily going to find the most compact way of doing things. So how do we prevent MATLib from blowing up when we get to that stage?
Yeah, so we're not at the point yet where LLM agents are allowing PRs into MATLib, are approving the PRs themselves. We might get there, but at the moment, it's human beings who are looking at every single PR. And right now, there's unfortunately, let's see, last I checked, there were what, 2,000 open PRs. So it's a extremely 2.1 thousand. There's 2.1 thousand pull requests. And the reason it's so many is because human beings are meticulously going through every single proposed contribution to the library, saying, is this the right abstraction? Does this do something that's already covered somewhere else in the library and the proposer didn't know? Is this LLM code, and should that LLM code be, more compact and so on? So right now, all of this work is being done by human beings. The contributions, by the way, are not always by human beings. There are a number of contributions already that have been by LLMs, or humans working with LLMs, of course. So
Yeah, so
So-
I'm thinking more of that, where like more and more of the contributions will be, largely constructed by LLMs. And I mean, at some point you can't just, I mean, you can hold the dam tight for only so long. At some point, in order to make further progress, you have to allow some of this code in. But then, then what, I mean, is it okay that mathlib, suddenly swells to, like trillions of lines of code, or is that actually going to cause problems?
Well, the hope is that Mathlib will swell to trillions of lines of code. The hope is that it won't cause problems, but again, we have to be extremely careful because already, when I'm working on the Fermat last theorem project, when you import something, that uses some really abstract technology, it can take Lean like 10 seconds to respond to a command. And once it takes 30 seconds to respond to a command, it's no longer an interactive theorem prover. It's very, very annoying to type something and then sit there for 30 seconds waiting for it to answer back. Like, if you talk to a really, really slow undergraduate, it's extremely frustrating. And if it's too frustrating, then you're going to stop doing it. It should be this fast, as quickly as it was responding to us here, giving us immediate feedback on what it understands and what it doesn't understand. So that in fact is one of the reasons why there was this major effort not so long ago to port things from Lean 3 to Lean 4. And people say, why don't you just make it backwards compatible? And the entire reason not to make it backwards compatible is that we're constantly improving the response. And you can't do that in a backwards compatible way. And human beings had to manually port things from Lean 3 to Lean 4. And God forbid there's going to be a Lean 5 someday. Hopefully not. Hopefully this is the final one and we don't have to do another one of these ports. But your point is really, really important. If we want things to grow in the library, we have to accept that LLMs are going to help us write these things. I mean, what I have in mind as a first pass is that had I tried to write all of this code, where was it? All of this code myself, just from scratch, I'd have to sit there and think about like, where is this in the library? How do I really want to say this? The LLM really speeds that up. But I'm still responsible for everything that I'm writing. The next level of that is I'm responsible for the statements. And then I check that the statement says what I want, and then the LLM suggests the proof. Lean says the proof is okay. Maybe I send it through Claude again and say, golf this. What's the right abstraction for this? What's the smallest version of this proof? So if you have lots and lots of agents talking to each other, then you get to the point where eventually some of these PRs are getting checked by an LLM agent that says, yep, this proof is good. It's nice and short. It's crisp. I've checked that it doesn't duplicate things in the library. I think we should let it in. And then maybe there's a final check where a human being looks over it and says, okay, you're not trying to, delete the library, and yeah, let it in. But you're absolutely right. I mean, once you give it an inch, it's going to take a mile.
Yeah, but maybe LLMs can help us with that too.
Exactly. They are the cause of the problem and also the solution to the problem, potentially. Yeah, thanks for that question. It's a really important point.
Okay, thank you. Any other questions? If no, I guess we can thank the speaker again. Yeah, thank you so much, Alex.
Thank you.
Thank you, Alex.
My pleasure.
Thank you for the wonderful talk, and thank you everyone for the great discussion. See you next week. Take care,
Bye.
everyone.
Yeah.
Bye.